Now that we've talked about some of the symbols that are involved in a chemical reaction, it's really time to start talking about the numbers. You may have noticed that a pretty standard part of most chemical equations is that there are big numbers out in front of some of the chemicals. How do they get there? Well, we're about to learn how. We're going to go through the process of something called balancing a chemical reaction. Now, where did this come from? Well, balancing chemical reactions is all born from one inescapable law, the law of conservation of matter. Now, if you don't remember what this law means, it simply states this, that matter can neither be created nor destroyed. It can simply be rearranged. Now, when you're taking a look at a chemical equation, what that really means for us is that the number of atoms on the reactant side has to absolutely equal the number of atoms on the product side. That means that matter was neither created nor destroyed, only rearranged. Now, when we're about to start this process, there are a few rules that we need to follow. First of all, you absolutely may never, ever, ever change a subscript. Those are the little numbers behind and down low for each atom. That is absolutely indicating the type of chemicals that we have present. If we change them, we're actually changing the bonds, and that's not good. So we absolutely never, ever, ever change one of the little numbers that are out behind, the subscripts. However, we can add numbers in, but we can only add in numbers in front of the chemical formulas. They will multiply in and through. We call these numbers that are out in front of the chemicals coefficients. Now, I want to be clear about how those work. A coefficient will modify the chemical that it's in front of, but it will stop its effect at either a plus sign or the arrow. So in other words, the little number in front of A will only affect A. The little number in front of B will only affect B, and the little number that's in front of AB will only affect AB, but it affects both that A and the B together. I want to make sure I'm very, very clear on what this really looks like. So let's go through counting the number of atoms when you have both subscripts and coefficients to deal with. Starting with this chemical formula, we have A, B with a subscript 3. How many of each atom would we have present? Well, I think that there's only one A atom and 3 B atoms. What's important to remember here is that a subscript will only modify the atom that it follows, only the atom that it's directly next to. And that gives us the 3 B atoms. Well, let's kick this up a notch. What about in this combination? Now I have both a coefficient and a subscript. Well, coefficients run on the distributive property. So the 4 will distribute both to the A and to the B. What that leaves us with is this idea that now I'm going to need to multiply some numbers together to get to my final answer. In this case, I would have 4 A atoms and 12 B atoms. How did I get to that 12? Well, notice that there were 2 numbers in there, and I needed to multiply them together to get to the total numbers of B. The 4 distributed to the B, and it already had the 3. Let's take a look at this more complicated chemical example. You're going to need to know how to handle polyatomic ions as well, and those can feel pretty complicated. Well, in this particular chemical example, we again need to use the distributive property. I want you to remember that the 2 that's behind the BO3, behind those parentheses, that actually distributes to anything inside the parentheses. It doesn't go all the way to the A, it only distributes to the things inside the parentheses. And Subscripts also multiply. So anytime that you're handling numbers on the inside of a chemical equation, they will always multiply together. In this example, I would have one A atom, two B atoms from the little subscript 2 that distributed in, and finally 6 oxygen atoms. Don't forget that the subscripts will multiply. Let's take a specific look at that oxygen. How did we get to 6? Well, the oxygen already had 3, and the additional subscript 2 distributed in, giving us a total of 6, because the numbers will multiply. All right, how about one more very complicated example? How about this? My goodness, look at all those numbers. All right, so what do? A couple reminders. First of all, both the coefficients and the subscripts will multiply. All of the numbers multiply together. We just need to figure out which numbers apply to which atoms. Well, the coefficient is going to distribute to absolutely everything in the formula. So the 4 is going to distribute to both the A, the B, and the O. Secondly, the subscript, particularly the 2, is only going to distribute to anything inside the parentheses. So the 2 will distribute to both the B and the O, but it will not distribute to the A. So what that leaves us with is that we're going to have 4 A atoms, 8 B atoms, and 24 oxygen atoms. How did we arrive at this? Well, taking a look at the B specifically, the coefficient 4 distributes to the B, and the subscript outside the parentheses also distributes to the B. 4 times 2 is 8. Well, what about the oxygen? The oxygen was a little bit more complicated. Now, don't forget that the oxygen already had a subscript 3. The 2 subscript outside the parentheses distributed to the oxygen, and the coefficient 4 also distributed to the oxygen. That gives us 4 times 2 times 3. That's 24 oxygen atoms. Now that we know a little bit more about how to handle the numbers on the inside of a chemical equation, it's time to make sure that we have the same number of atoms on each side of the equation. It's time to balance an equation. Let's take a look at a pretty simple example. Here's my first example. H2 plus O2 makes H2O. Now, when I go through and I balance a chemical equation, I find it pretty useful to make a little list of the number of atoms I have on each side. So I'll start with the reactant side. And I notice that I have 2 H atoms, and I also have 2 oxygen atoms. On the product side, I have 2 hydrogen atoms and only 1 oxygen atom. My job in balancing is to make sure that I have the same number on each side. I have to add coefficients in, the multipliers in the front of these chemicals, to make sure that I can match them from one side to the other. Now I notice that the oxygen atoms are mismatched. I have 2 oxygen atoms on my reactant side and only 1 on my product. What that means that I'm going to have to do is to put a coefficient in front of the chemical formula until they match. The coefficient I'm going to put in is a 2. Now don't forget though that multiplies into both the hydrogen and the oxygen. So on the product side now, that leaves me with 4 hydrogen atoms and 2 oxygen atoms. And that's okay. This is very normal when you're balancing equations, that you might fix one atom but throw another atom out of whack. So repeat the process again. Let's see if we can fix our newly created problem. So I have 2 hydrogen atoms on the reactant side and 4 on the product. Can I fix it? Sure. Throw a coefficient 2 in front of the reactant hydrogen. And again, don't forget that that's going to multiply in and through and leave us with 4 hydrogen atoms. Well, guess what? Your equation is now balanced and we're complete. Let's try another example. Again, I'm going to start with listing the number of atoms I have on each side. So on my reactant side, I only have 1 iron atom, but I have 2 chlorine atoms. On the product side, I have 1 iron atom and 3 chlorine atoms. Let's start to try and make this even out. I notice that my issue is with my chlorine atoms. And this can be kind of confusing as to how to figure out how to even it out. If it's not immediately obvious, I usually go with the tactic of cross-multiplying. So I'm going to provide the 3 coefficient on my reactant side and the 2 coefficient on my product side, giving me a total of 6 chlorine atoms on both sides. Now don't forget that by doing that, I may have affected other atoms. On my product side, that brings up my total iron atoms to 2, throwing them out of balance. Now I have to fix that. So I have 1 iron atom on my reactant side and 2 iron atoms on my product side. How do I fix it? How about we throw a coefficient 2 in front of the reactant iron? And now you'll notice my equation is balanced. Now, when you're balancing a chemical reaction, there are a couple tips and tricks that may actually save you a bit of time and heartache. First of all, you may want to try to balance any polyatomic ions that are inside of your formula as a major unit. Now remember that those things are bonded with covalent bonds, and they're a little harder to break during the course of a chemical reaction than an ionic bond. The ionic bonds tend to want to rearrange a little easier than the polyatomic ions. Second, work from left to right and be methodical about that, and constantly go back and double check your work. Oftentimes, I actually go back and start from the beginning just to make sure that the work that I have kept on doing still applies and it hasn't really messed up my problem. Third, always make sure that you reduce to lowest terms. So for example, if you notice that the only way that things worked out was by adding in the coefficients of 2s and 4s, and everything has a 2 or a 4 in front of it, reduce that back to its lowest terms, and that's okay. It's the same thing that we do with chemical formulas. It also applies to balancing chemical equations. And finally, I have often found it pretty useful to visualize H2O, water, instead as the chemical formula HOH. It still has the same exact number of atoms, it's just rearranged in a little bit of a better way to make it make more sense for our brains to operate with. I want to give you a specific example with this and also how to work with polyatomic ions. So let's take a look at a more specific example. Here's a great one. Now, I'm going to start by labeling the number of atoms that we have on each side. But when I do that, I'm not going to break apart my polyatomic ions. I'm going to list them like they were their own atom. So on my reactant side, that would give me 1 copper atom, 2 hydroxide polyatomic ions, 3 hydrogen atoms, 1 phosphate polyatomic ion. Now I have an issue. On my product side, I have a mismatch here. I don't see hydroxide yet. That's going to be really hard to balance. But then I remember the rule. Visualize H2O instead as HOH. Oh wait, there's my hydroxide ion. Now things are going to be a little bit easier to balance. So let's list the pieces on my product side. So now I have 3 copper atoms, I have 1 hydroxide ion, 1 hydrogen atom, and 2 PO4 atoms. Now notice I chose to write these down in the same order as my reactants. I didn't necessarily work from left to right here. And that's just simply for convenience. And I think you're going to see why in just a moment. Now let's go methodically straight down this list. That would essentially be the same as working from left to right, starting on the reactant side. So I notice that I'm mismatched with my copper. I only have 1 on the reactant side and I have 3 on the product. So let's add the coefficient 3 in front of my CuOH2. Now don't forget that that does distribute to both the copper and the hydroxide, so I need to fix my numbers. That would give me 3 copper atoms and 6 hydroxide polyatomic ions. Let's move to the next item on the list, hydroxide. I have 6 on the reactant and 1 on the product. I need to fix that. I'll do that by adding a 6 in front of my HOH, my water. Don't forget, though, that that 6 coefficient distributes to both the hydrogen and the hydroxide. That's going to shift my numbers. So I'll modify both of those. My hydroxides match, but now my hydrogens do not. So the vicious cycle continues. I'll fix this by adding a coefficient 2 in front of my H3PO4, my phosphoric acid. And again, don't forget that that 2 is now going to distribute to both the H and the PO4, so that will shift my reactant side numbers. Now my hydrogens match. Let's double check to make sure our phosphates match as well. And what do you know? At the end of the balancing act here, everything matches beautifully. At this point, we could actually say that the equation is balanced.